Hello and welcome back. In the last video, I talked about physical properties and some uses of carbonyl compounds. In this video, we will see some chemical reactions of carbonyl compounds. First, let us see the contents. We will start off with something called as nucleophilic addition reactions, which include addition of hydrogen cyanide, addition of sodium hydrogen sulfide, addition of Grignard reagents, addition of alcohols, and finally addition of ammonia and its derivatives. Then we will see reduction, which includes reduction to alcohols, reduction to hydrocarbons. Next, oxidation, which includes Tollens test, Fillings test, oxidation of methyl ketones by haloform reaction. Then we will move on to reactions due to alpha hydrogen, which has aldol condensation and cross aldol condensation. Finally, we will see some miscellaneous reactions that has Carbonyl reaction and electrophilic substitution reaction. So let's get started with nucleophilic addition reactions. First, we will see what are these. Contrary to electrophilic addition reactions observed in alkenes, aldehydes and ketones undergo electrophilic addition reactions. So before moving on to the reactions themselves, first we will see the mechanism, then the reactivity of carbonyl compounds for this reaction, and then finally we will see some examples that were listed earlier. So let's start with the mechanism. So how does the reaction start? A nucleophile attacks the electrophilic carbon atom of the polar carbonyl group from a direction approximately perpendicular to the plane of sp2 hybridized orbitals of carbonyl carbon. So this is how it takes place. We have a nucleophile and it attacks a carbon atom and we get an intermediate, that is tetrahedral. Initially the compound was planar, but after the attack we get a tetrahedral intermediate because there are 4 atoms surrounding the carbon atom now. So let me put it in words. The hybridization of carbon changes from sp2 to sp3 in this process and a tetrahedral alkoxide intermediate is produced. Now what's next? This intermediate captures a proton from the reaction medium to give electrically neutral product. So the intermediate has now captured a proton, and after the step 2 we get the addition product, that is electrically neutral. So this is the mechanism of nucleophilic addition. The net results in addition of nucleophile and H plus around the carbon oxygen double bond. Now we will see how these carbonyl compounds are reactive, that is the reactivity of these carbonyl compounds towards nucleophilic addition reactions. Aldehydes are generally more reactive than ketones in nucleophilic addition reactions due to steric and electronic reasons. So we have 2 reasons over here. One is steric and other one is electronic reasons, due to which aldehydes are more reactive than ketones. Sterically, the presence of 2 relatively large substituents in ketones hinders the approach of nucleophile to carbonyl carbon than in aldehydes having only one such substituent. Electronically, aldehydes are more reactive than ketones because 2 alkyl groups reduce the electrophilicity of the carbonyl carbon more effectively than in former. So we have seen that aldehydes are more reactive than ketones in nucleophilic addition reactions, and we had seen 2 reasons now. One is steric reason and the other one is electronic reasons. So before moving on to the reactions, let's do a small question. So this is the problem. Would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reactions than propanol? We had discussed 2 reasons earlier. Think about this one now. I'll give you 10 seconds and you can pause the video if you want more time. Okay, now let's solve it together. The carbon atom of the carbonyl group of benzaldehyde is less electrophilic than carbon atom of the carbonyl group present in propanol. The polarity of carbonyl group is reduced in benzaldehyde due to resonance and hence it is less reactive than propanol. I hope this question is clear. Now let's look at some examples of nucleophilic addition reactions of carbonyl compounds, starting with addition of hydrogen cyanide. Aldehydes and ketones react with HCN to yield cyanohydrins. The name of the product is called cyanohydrins. This reaction occurs very slowly with pure HCN. Therefore, it is catalyzed by a base and the generated cyanide ion, that is Cn-, being a stronger nucleophile, readily adds to the carbonyl compounds to yield corresponding cyanohydrin. So this is the reaction. We have HCN, we give it with a base to catalyze the reaction, we get Cn-, which is strong nucleophile, and now the Cn- attacks the carbon atom of the carbonyl group to get the addition product. We get a tetrahedral intermediate as expected. I hope this one is clear. Now let's see addition of NaHSO3, that is sodium hydrogen sulfide. Sodium hydrogen sulfide adds to aldehydes and ketones to form the addition product. So this is what happens. We have an carbonyl group treated with NaHSO3, we get the tetrahedral intermediate, and with proton transfer we get the addition product. The position of the equilibrium lies largely to the right side for most aldehydes and to the left for most ketones due to steric reasons. So this means ketones are less reactive towards addition of NaHSO3 due to steric reasons. So the equilibrium lies in the left side for most of the ketones. However, aldehydes it's in the right side because they are pretty good reactive. The hydrogen sulfide addition compound is water soluble and can be converted back to the original carbonyl compound by treating it with mineral acid or alkali. Therefore, these are useful for separation and purification of aldehydes. While if I treat this hydrogen sulfide addition compound with a dilute mineral acid or alkali, I get back the aldehyde. So, it is used for separation and purification of aldehydes. Next is addition of Grignard reagent or MgX. We have seen this already in unit 11 of class 12. So I am moving on to addition of alcohols now. Aldehydes react with one equivalent of monohydric alcohol in the presence of dry hydrogen chloride to yield alkoxy alcohol intermediate known as hemiacetals, which further react with one more molecule of alcohol to give geminal dialkoxy compounds known as acetal. So in this you need to know what is an hemiacetal and what is an acetal. Hemiacetal is alkoxy alcohol intermediate that you get, and the acetal is geminal dialkoxy compound that we get. So this is the reaction. I take aldehydes with one equivalent of monohydric alcohol. Monohydric means one OH group in it. And in the presence of HCl gas, I get an hemiacetal, and on further reaction with one more molecule of alcohol, I get a geminal dialkoxy compound, that is an acetal. Yeah. Ketones react with ethylene glycol under similar conditions to form cyclic compounds known as ethylene glycol ketols. So I have got an ketone over there as COR, and I treat it with ethylene glycol, that is CH2OH, CH2OH. In the presence of HCl gas, I get ethylene glycol ketol. That is a structure in the product, the first one in the product, that's called ethylene glycol ketol along with byproduct water. Dry hydrogen chloride protonates the oxygen of the carbonyl compounds and therefore increases the electrophilicity of the carbonyl compound, facilitating the nucleophilic attack of the ethylene glycol. So that's why we used hydrochloric acid in the previous reaction. Acetals and ketols are hydrolyzed with aqueous mineral acids to yield corresponding aldehydes and ketones respectively. Finally, addition of ammonia. Nucleophiles such as ammonia and its derivatives add to carbonyl group of aldehydes and ketones. Derivatives I mean H2NZ, where Z is an alkyl, aryl, OH or NH2 as I have given below, such groups. So these are called derivatives of ammonia. The reaction is reversible and catalyzed by acid. The equilibrium favors the product formation due to rapid dehydration of the intermediate to form C double bond NZ. That's an intermediate. So we will see some examples of this reaction where Z is the same Z we've seen in the last slide, NH2Z, that's Z, and we will see what the reagent name is, then we will see what the carbonyl derivative that we get, and we will name the product after that. So first the line is H, that is called ammonia because H2NH is NH3 and it's apparently ammonia. And the carbonyl derivative I get is C double bond NH and it's called imine. Next, RNH2, that's an amine. We will see this in the next video. You will see this in the next unit. And the carbonyl derivative is CNR. This is known as substituted amine and this is commonly known as Schiff's base. Next, NH2OH, hydroxylamine. C double bond NOH is the carbonyl derivative that we get and it's called oxime. NH2NH2, hydrazine, C double bond NH2 is the derivative and this is known as hydrazone. Hydrazine, hydrazone. Yeah. If the Z is HN phenyl group, that is NH2, NH and C6H5, then it is known as phenyl hydrazine. Last step it was hydrazine. Now we substitute an H with a phenyl group. Now it's known as phenyl hydrazine. And we get a similar derivative and the product is similarly called phenyl hydrazone. If we have NH2, NHCO, NH2, it is called semi-carbazide and we get the product as semi-carbazone. Now this is an important one, that's why I gave a full picture of it. So if the Z is HN with a phenyl group substituted NO2 like that, which is known as 2,4-dinitrophenyl hydrazine, and I get 2,4-dinitrophenyl hydrazone. So why is this important? 2,4-DNP, dinitrophenyl, is known as DNP in short. 2,4-DNP derivatives are yellow, orange or red solids and hence these are useful for characterization of aldehydes and ketones. So these are used for recognizing the presence of carbonyl group, both aldehydes and ketones in a compound. So when we treat a compound with 2,4-DNP derivatives, if the product that you get is yellow, orange or red, then it is a test for presence of aldehyde and ketones. Yeah. So with this we have completed nucleophilic addition reactions. Now let's move on to reduction, and first in that is reduction to alcohols. Aldehydes and ketones are reduced to primary and secondary alcohols respectively by sodium borohydride, that is NaBH4, or lithium aluminum hydride that we have seen many times, LiLH4, as well as by catalytic hydrogenation that we have seen in unit 11 of class 12. Reduction to hydrocarbons. The carbonyl group of aldehydes and ketones is reduced to CH2 group on treatment with zinc amalgam and concentrated hydrochloric acid. This is known as Clemmensen reduction. So this is an example. We have CO group, and when I treat it with zinc amalgam, that is ZnHG, in the presence of concentrated hydrochloric acid, I get the reduction of CO group to CH2 group, and this is known as Clemmensen reduction. Otherwise, you can also do this. I can treat it with hydrazine followed by heating with sodium or potassium hydroxide in high boiling solvents such as ethylene glycol, and this is known as Wolff-Kishner reduction. So we have the example over here. We have CO group treated with hydrazine, that is NH2NH2, in the conditions given above, then I get a CH2 group at the last after another step with KOH or ethylene glycol in heat. So these are the two methods to reduce carbonyl compounds, that is the carbonyl groups to be more precise, to hydrocarbons. One is Clemmensen reduction and other is Wolff-Kishner reduction. Now let's go to oxidation. Aldehydes differ from ketones in their oxidation reactions. Aldehydes are easily oxidized to carboxylic acid on treatment with common oxidizing agents like nitric acid, potassium permanganate, potassium dichromate, Even mild oxidizing agents, mainly Tollens reagent and Fellings reagent that we will be seeing in the coming slides, also oxidize aldehydes. So we have RCHO. In the presence of strong oxidizing agents, I get RCOOH. In fact, even with mild oxidizing agents like Tollens and Fellings reagent, I also get a similar RCOOH oxidation. Ketones are generally oxidized under vigorous conditions, that is, strong oxidizing agents and at elevated temperatures. Their oxidation involves carbon-carbon bond cleavage to afford a mixture of carboxylic acids having lesser number of carbon atoms than the parent ketone. So if I have RCH2COCH2R and I treat it with a very strong oxidizing agent at some elevated temperatures, there are two possible products possible. I mean, like two different types of reactions possible. One, I can get RCOOH and R-CH2COOH. Here the bond cleavage is in the left side, and otherwise I can get the bond cleavage in the right side to get RCH2COOH and R-COOH. Now let's focus on mild oxidizing agents. So the mild oxidizing agents given below are used to distinguish aldehydes from ketones. We already seen one distinguishing test, that is to differentiate carbonyl compounds from other groups, that is using 2,4-DNP. And now here is to distinguish between aldehydes and ketones themselves. So first is Tollens test, Fellings test, and oxidation of methyl ketones by haloform reaction. Tollens test first. On warming an aldehyde with freshly prepared ammoniacal silver nitrate solution, that is Tollens reagent, a bright silver mirror is produced due to the formation of silver metal. So what is Tollens reagent? Ammoniacal silver nitrate solution. And Tollens test is this result of getting a bright silver mirror when you treat an aldehyde with Tollens reagent. And why is a bright silver mirror formed? Because of formation of silver metal. The aldehyde or oxidized to corresponding carboxylate anions. The reaction occurs in alkaline medium. So now let's look at the reaction. We have RCHO, AgNH3 twice plus, that is your ammoniacal silver nitrate, and in presence of an alkaline medium OH minus, I get RCO minus, that is carboxylate anion, with silver, that gives a silver mirror, and H2O and 4NH3. That's with Tollens test. Now we will move on to Fellings test. Fellings reagent comprises of two solutions, Fellings solution A and Fellings solution B. So this Fellings reagent has two solutions, A and B. What is A and what is B? Let's look at them now. Fellings solution A is aqueous copper sulfate. Fellings solution B is alkaline sodium potassium tartarate, that is Rochelle salt. These two solutions are mixed in equal amounts before the test. So to do this test, we mix Fellings solution A and B in equal amounts. On heating an aldehyde with Fellings reagent, a reddish brown precipitate is obtained. So the presence of a reddish brown precipitate is a confirmation of an aldehyde present in that compound. Aldehydes are oxidized to corresponding carboxylate anion. Aromatic aldehydes do not respond to this test. So if you need to differentiate between aliphatic and aromatic aldehyde, you can do Felling's test. So this is an example, RCHO in terms of 2Cu plus, that is coming from the Felling's reagent, and 5OH minus gives RCO minus, that's the carboxylate ion, Cu2O, that is responsible for the reddish brown precipitate along with 3 moles of water. Next, we will see haloform reaction. Aldehydes and ketones having at least one methyl group linked to the carbonyl carbon atom, methyl ketones for example, are oxidized by sodium hypohalite to sodium salts of corresponding carboxylic acids having one carbon atom less than that of a carbonyl compound. The methyl group is converted to haloform. The oxidation does not affect a carbon-carbon double bond if present in the molecule. Iodoform reaction with sodium hypoiodide is also used for detection of CH3CO group or CH3CHOH group, which produces CH3CO group on oxidation. That is, if you have a CH3CHOH group and we treat it with haloform reaction reagent, that is sodium hypohalite, you get an oxidation of CHOH group to and ketone. Indirectly, you have a methyl ketone over there. So this group CH3CHOH also gives haloform test. So this is the reaction RCOCH3. We need a methyl group of CH3. In presence of NaOX, that is sodium hypohalite, you get RCOONA, that is the carboxylate salt, along with CHX3, that is your haloform. X can be Cl, B, or I. So you can get a chloroform, bromoform, and iodoform. Similarly, you have another reaction. So before moving on, we have learnt a lot. So why not try a question? So this is the second problem in this video. An organic compound A with molecular formula C8H8O forms an orange-red precipitate with 2,4-DNP reagent and gives yellow precipitate on heating with iodine in the presence of sodium hydroxide. It neither reduces Tollens or Felling's reagent, nor does it decolorize bromine water or Bayes reagent. On drastic oxidation with chromic acid, it gives a carboxylic acid B having molecular formula C7H6O2. Identify the compounds A and B and explain the reactions involved. I will give you 20 seconds. You can pause the video if you need more time, and after that we will discuss the solution. Okay, let's discuss the solution. A forms 2,4-DNP derivative, therefore it is an aldehyde or ketone. Since it does not reduce Tollens or Felling's reagent, A must be ketone. A responds to iodoform test, therefore it should be a methyl ketone. The molecular formula of A indicates high degree of unsaturation, yet it does not decolorize bromine water or Bayes reagent. This indicates the presence of unsaturation due to an aromatic ring. Compound B, being an oxidation product of a ketone, should be a carboxylic acid. The molecular formula of B indicates that it should be a benzoic acid, and compound A should therefore be a monosubstituted aromatic methyl ketone. The molecular formula of A indicates that it should be a phenyl methyl ketone, that is acetophenone. So this is how we are going to come at the solution of A and B. We are going to analyze everything that is given in the question, and finally we will deduce what A and B are. So let's finish this question with the reactions that they are asked for. So this is the first reaction. The compound with 2,4-DNP gives the component I write that we have seen already before. It does not give Bayes test, it does not decolorize bromine water, it doesn't give Felling's test, nor does it give tolerance test. So we don't have to write those reactions. Directly we can write A with iodoform reaction gives the corresponding iodoform and the acetate salt of sodium, and upon oxidation with the given compound we get a benzoic acid. That is, oxidation with chromic acid we get benzoic acid. This is pretty simple, right? Okay, let's move on. Reactions due to alpha hydrogen. The aldehydes and ketones undergo a number of reactions due to acidic nature of alpha hydrogen. By the way, I hope you know what an alpha hydrogen is by now. That is the hydrogen attached to the neighboring carbon of the carbonyl group. So if we have RCH2 CHO, that H2 that is to the left of CHO is called alpha hydrogen. The acidity of alpha hydrogen atoms of carbonyl groups is due to strong electron withdrawing effect of the carbonyl group and Western stabilization of the conjugate base. So this is how the Western stabilization takes place. So first and important reaction is aldol condensation. Aldehydes and ketones having at least one alpha hydrogen undergo a reaction in the presence of dilute alkali as catalyst to form beta hydroxyaldehydes, which are known as aldol, or beta hydroxy ketones, which are known as ketol, respectively. So what is the condition over here? Aldehyde ketones, at least one alpha hydrogen, in presence of dilute alkali as catalyst gives beta hydroxyaldehydes, aldol, or beta hydroxy ketones, ketone, respectively. This is known as aldol reaction. So we are not done condensation yet. This is just aldol reaction. For example, ethanol, NaOH gives aldol. That's an aldehyde we have taken, and now ketone, propanone, that is in this case, with alkali like barium hydroxide gives ketol. The name aldol is derived from the names of the two functional groups, aldehyde and alcohol, present in the products. Yeah? The aldol and ketol readily lose water to give alpha, beta unsaturated carbonyl compounds, which are aldol condensation products, and the reaction is called aldol condensation. So what has happened over here? We have taken an aldehyde or ketone with an alpha hydrogen. We have treated it with dilute alkali as catalyst. It forms a product, that is beta hydroxyaldehydes, aldol, or beta hydroxy ketones, which is called as ketol. And these aldols and ketols readily lose water to give an alpha, beta unsaturated carbonyl compounds, and this is called as condensation products, and hence the name aldol condensation. Now let's look at the complete reaction. We had ethanol in the previous case first, and we treated it with NaOH. We got an aldol, and when this aldol loses water, we get butanol, that is CH3 CH double bond CH CHO. Similarly, propanone with barium hydroxide, we got a ketol before, and when we heat that again, we get an alpha beta unsaturated carbonyl compounds. So how do we write this condensation products easily? So this is a simple technique that I want to show you. Suppose I have an aldehyde like this. I write it like this. So in this case, I have taken RCH2CHO, any general aldehyde with an alpha hydrogen. Here there are two alpha hydrogens. For sake of simplicity, I have taken two alpha hydrogens. So by the way, for condensation, we need two alpha hydrogens. Yeah. So we have two alpha hydrogens here, and when you write it like this, you just draw a box about H2O. Okay. H2O is lost, and directly now a double bond is pending, and you just bond those two compounds and you get something like this. That is the condensation product. Yeah, simple. Okay, though ketones give ketols, the general name aldol condensation still applies to reactions of ketones due to the similarity with aldehydes. Pretty biased. Okay, now let's go to cross-aldol condensation. When aldol condensation is carried out between two different aldehydes and ketones, it is called cross-aldol condensation. Why cross? We will see. If both of them contain alpha hydrogen, it gives a mixture of four products. Why cross again? We have two different aldehydes and our ketones. So you can have one aldehyde, one ketone, one aldehyde, or two ketones reacting together. And if both of them have alpha hydrogens, we have four possible products like this. So from two molecules of ethanol, we get the above one, that is simple or self-aldol products. And from one molecule of ethanol and one molecule of propanol, we get cross-aldol products. You can get this product similarly like how we have done in the previous thing, how like I showed you a technique, right? You can do that to directly get the condensation products. Ketones can also be used as one component in cross-aldol reactions like this. So in this we have taken an aldehyde, one ketone, and we got a cross-aldol reaction. Finally, to some miscellaneous reactions. First in that is Cannizzaro reaction, which is also equally important as aldol reaction. So Cannizzaro reaction. Aldehydes which do not have an alpha hydrogen undergo self-oxidation and reduction, that is a disproportionation reaction on heating with concentrated alkali. So for aldol reaction, we needed at least one alpha hydrogen. Here, it should not have an alpha hydrogen. It should not have. And previously we took an dilute alkali. Here we take an concentrated alkali. In aldol condensation, we got a ketol or an acetal. Here we get a self-oxidation and a self-reduction reaction. That's a disproportionation reaction. So let's see what happens. In this reaction, one molecule of aldehyde is reduced to alcohol while the other molecule is oxidized to carboxylic acid salt. For example, I have formaldehyde and I treat it with concentrated KOH and I heat it a little. I get methanol, that is a reduced product, and potassium formate, that is an oxidized product. Oxidized product is carboxylic salt of potassium here, since I have used KOH. So I get potassium formate. One more reaction, I have benzaldehyde in presence of concentrated NaOH. So NaOH, Na, we get a carboxylic acid salt of sodium. So as expected, you get benzyl alcohol and sodium benzoate. Yeah. Finally, electrophilic substitution reaction. Aromatic aldehydes and ketones undergo electrophilic substitution at the ring, in which the carbonyl group acts as a deactivating and meta-directing group. So the carbonyl group is deactivating and it is meta-directing. So for example, I have benzaldehyde, same reagents HNO3, H2SO4, 273 to 283 Kelvin. I get a meta substitution over here. And similarly, you can write other reactions for yourself. So with this, we have come to the end of this video. To summarize, we started off with nucleophilic addition reactions, which had reactions like addition of HCN, NaHSO3, Grignard reagent, alcohols, and ammonia and its derivatives. Then we studied about reduction reactions of carbonyl compounds. Then we moved on to oxidation, which had mild oxidation reagent tests like Tollens test, Felling's test, and haloform reaction. Then we saw reactions due to alpha hydrogen, which had aldol reaction and cross-aldol condensation. Finally, we saw some miscellaneous reactions, which had Cannizzaro reaction and electrophilic substitution. With this, we have also finished carbonyl compounds. In the next video, I will be starting off with carboxylic acids, mainly nomenclature, structure of carboxyl groups. Then we will see physical properties and maybe even some techniques to prepare carboxylic acids. I hope you found the content in this video useful, and I have not solved many questions for this video because we have learned a lot of reactions and you need to read them first before solving some questions. So I have not taken any questions for now. There are plenty of questions in the NCERT book which you can go to after studying each of them. And yeah, that is pretty much it. Hope to see you in the next video. Goodbye.